Hello, friends. Welcome to the ATC Double Cut. Today, I am going to discuss an experiment that I did when I was in graduate school. And it was in my final year of graduate school, and I'd already done all kinds of field experiments about soil testing, different soil testing methods, and different potassium application rates. I'd done a field experiment over multiple years on an L93 putting green, and I also collected a whole bunch of sands. And as I collected these sands, I realized, wouldn't it be interesting to grow grass in them and see what happened? So I applied a lot of the things that I'd learned in the first few years of graduate school in this experiment that I did at the end. So this is chapter 7 in my dissertation, and you can find that on the Turfgrass information file. There's a link to that on the ATC website at asianturfgrass.com. So I will put a direct link to the blog post that I'm talking about here in my in the show notes. And you can also go to asianturfgrass.com and go to the library section of asianturfgrass.com. If you go to the library section of asianturfgrass.com, then you can use an article filter to search the library, and you can go through and find my dissertation. Let's see if I can do that. I'll just go by date. That was published in 2006. So if we go back there, boom, there it is. 2006, non-acid cation bioavailability in sand root zones. If I click on that, what does that bring us to? It brings us to a PDF. If I click on that, it brings up another link. Right. So it brings up the Turfgrass information file. This is all available, and you can find all of these links for chapter 1, chapter 2. The ones that I think are really interesting, uh, chapter 6 and 7. Chapter 6 is a simple method for predicting cation exchange capacity with special respect to sand root zones. That was one of my favorite projects that I was working on, was about cation exchange capacity. And then this one was chapter 7, assessing the availability of non-acid cations to creeping bent grass in sand root zones. That's the one that I'm going to talk about today, and some of the details of that experiment are reported in that particular chapter. So let's go back to where we were on the ATC website. I want to look at this post called Soil Nutrient Levels Change. And this is something that I am so passionate about. I've been working on this for like 25 years. And this is a post that I felt like, I feel like everybody should know this, but I sense somehow that some people don't know this, or they don't realize how important it is to recognize that the grass is growing in a soil where the nutrient levels change, and the nutrient levels might change more rapidly than you expect. Now, it depends on the soil, and it depends on the climate, and it depends on how you're managing the grass, and it depends on which nutrient we're looking at. It depends on all of those things. And did I say soil type? It certainly depends on the soil type. It depends on all of those things, on how much and how rapidly the soil nutrient levels will change. But in the case of sand root zones, and in the case of potassium, which is what I'm talking about specifically in this blog post, things can change quickly. So what I don't recommend, what I think is a problem, and it's a risky problem because it would give you a false sense of security. If you test the soil and you find that potassium is at a relatively high level, let's say that your potassium is at 75 parts per million in the soil on a Mehlich 3 extractant, and you think, wow, that's double the MLSN minimum, that is higher than average for sand root zones, and to make a decision just based on that number only, saying I have enough, I don't need to apply fertilizer, that is the wrong way to do it. I am convinced that's the wrong way to do it, and I've written a lot of blog posts about it, and I keep trying to explain this year after year after year, and I still read book chapters, or I read scientific articles, or I hear presentations from other people teaching about how to make fertilization decisions for fine turf grass. And I hear them sometimes talk about soil test levels as if they are static, but they are not static because the grass grows, the roots take up nutrients, and the soil test levels they change, and they only change in one direction. They go down. They go down because the grass roots take up nutrients and remove nutrients from the soil. And that is a process that causes soil nutrient levels to go down. So the soil nutrient levels change. And I remembered that this experiment that I did in 2005 was a short experiment. It was just 65 days long. And I remembered I had data of how the soil potassium levels changed. I have data on how a lot of soil nutrient levels changed, but it was it was one where potassium changed a lot, and each of these four different sands had a different starting potassium level. So I want to describe this and try to clarify two particular things that you want to remember. And I'm not saying soil testing is not useful. I think soil testing is really useful, but use soil testing in conjunction with an estimate of how much the grass will use, and use soil testing not as a criterion of I'm okay or I'm not okay. Don't use soil testing as something where you're trying to find these target levels that you're trying to hit in the soil, or use soil testing so you can find out how much you need to eat, how much of how much potassium you need to add to try to put soil potassium at some kind of target level. That's not how it should work at all. What should be done, what I recommend, is use soil testing as a way to determine how much fertilizer to apply, not to feed the soil, but to feed the grass with enough nutrients, because the soil is going to hold as many nutrients as it's going to hold. The soil doesn't have a widely varying ability to hold different amounts of nutrients. So if your soil doesn't have a lot of potassium in it, then it probably can't hold a lot of potassium. So just adding potassium to try to hit some level that you would like to have in the soil, that is pointless. And then if you stop adding potassium, the potassium would just decrease rapidly, and it goes back to a level that might not be sufficient to supply potassium to the grass. But what does make sense is recognizing that your soil would be a little bit low in potassium, then you add enough as fertilizer to make sure that your grass always has enough. So that's how I use soil testing. That's how MLSN works, and it works really well. And I think uh, sometimes people either haven't studied soil testing so much, so they're not quite sure about how it works, and they get a few things wrong, or they're using a way of thinking about soil testing that was developed for agricultural soils, for agricultural crops, not for turf grass, but for agronomic crops, not for turf grass. And it was developed in, say, the 1960s or the 1970s. It was developed a long, long time ago. And that just kind of persists. That type of thinking persists. And it's one of the reasons why I'm not so keen. There was a discussion recently about the word agronomy and agronomists, and I'm not so keen on calling turfgrass management agronomy, because if you use that type of agronomic thinking and it just persists from the 60s, 70s up to today, it leads to some inefficiencies in the way that turfgrass could get managed and fertilizer gets applied. So anyway, that's not what the topic is. The topic is about soil nutrient levels change. So let's get to it. This is a picture. I'm showing a picture of containers. These are from Oregon, and they are used to plant tree seedlings. And these ones were 4 inches or 10 centimeters deep. So it's the same depth as a sand root zone, and each one of these had a volume of about 50 cubic centimeters. So that's the amount of soil that was placed in each of these, and I used four different sands. One sand was from a sandy site on Long Island that has a excellent golf course now. One sand was from golf course putting greens at a golf course in the American Southeast. One sand was from a sand that's used to make putting greens on a golf course in the American West. And one sand was the sand that was used in New York near where I was working at Cornell University. So there's 4 different sands. Each of them are real sands that were taken from turfgrass sites or from sites that uh, they were either on-site sands for golf courses, or they were sands that were brought in and used as putting green root zones from which I collected these samples. So they're real sands that are used for golf course putting green turf, and they had a range of pH, a range of potassium levels to start. And so I took these sands and I put them in these containers, and then I planted Pen A1 creeping bent grass. I grew it from seed, and I fertilized with ammonium sulfate and monoammonium phosphate. So the grass had plenty of nitrogen, plenty of sulfur, and plenty of phosphorus, but it wasn't getting any potassium whatsoever. It was getting no potassium as fertilizer, and I knew what the starting um, I knew what the starting soil test levels were, and then I grew the sand, and then I destructively harvested some of these pods, or some of these containers at 35 days after planting, and then at 50 days. So 15 days later, I destroyed some more at 50 days after planting. And by destroying, I mean I cut off all the grass so I can measure what was in the leaf tissue and measure how much clipping production there was, how much above ground growth there was, and then I destroyed the soil so I could test it. And then I did the final harvest, destroying the remaining containers at 65 days after planting. So this experiment went from the time of planting to the day of the final harvest was 9 weeks and 2 days. And that is not a long time, but the soil potassium changed a lot. I made a chart of this that you'll find in the blog post, and there's a direct link to the blog post in the show notes. And the starting potassium levels at day 0 range from 20 parts per million on the Malick 3 test up to 80 parts per million. So that's a 4-fold difference. One of these sands started below the MLSN guideline. 3 of the sands started above the MLSN guideline. And remember, no potassium fertilizer was applied. And the silica sand, the one that's labeled GA, it started at 71 parts per million. In 35 days, it dropped all the way down to 24 parts per million. So in just about a month, just over a month, it dropped from 71 parts per million all the way down to below the MLSN guideline. And I wasn't leaching these. I was applying water with a syringe based on the gravimetric loss, on the mass loss of the sample. So I was just filling it back to field capacity, and I was catching all the leachate, which there wasn't any leachate, but I was very careful with this to make sure that I wasn't leaching the potassium out of the soil. So these containers were placed in a graduated cylinder, in another type of tube that would catch any water if any water did drain out the bottom of the pots, but drain out the bottom of the container, but it did not because of the way that I was irrigating. So this drop in potassium means that potassium was going into the plant, and so it wasn't in the soil anymore. And the other sands didn't drop so much, but they all went down. The BD sand dropped by 23 parts per million in the first 35 days. The CU sand dropped by 14 parts per million in the first 35 days. And the SK sand, which started really low, it dropped down to 12. So it dropped 8 parts per million. It went from 20 down to 12 parts per million in the first 35 days. So it changes rapidly, and that's why when people say, "Oh, if you they'll say something like, if you want to grow POA and have reduced risk of anthracnose, or if you want to be safe with anthracnose, then you want to have like 50 parts per million. You want to grow at 50 parts per million. But the thing is, if you start off at 50 parts per million, you could be down to 30 parts per million in a month. So at 50 parts per million, in order to stay at 50 parts per million, you need to add potassium fertilizer. And that's what I want people to understand is don't look at things like the MLSN minimum, which is 37 parts per million for potassium. Just don't worry about it. Don't look at that as like above 37 parts per million, you don't need to add potassium. Below 37 parts per million, you do need to add potassium. That's not how it works. The way that it works is you make a fertilizer recommendation based on the soil test result, and that is just a number that gets plugged in there. Now, I understand that I fail miserably at explaining this to a broad audience, but one person who does understand this very well is Jason Haynes, the golf course superintendent at the Sunshine Coast Golf and Country Club in British Columbia. He's so he understands this really well, and he explains it in a way that's different than the way I explain it, which I appreciate that. And Jason just wrote a blog post recently where he talks about how to think of this. And I will put a direct link to his blog post also, so that you can check that out and hear this, or read this when it's explained another way. Because I don't know what it is. I think because I've been working on this for so many years, and I did experiments like this when I was in graduate school, and it's just so clear to me. It's difficult when I understand it like this to explain it, especially when people have been taught about soil testing. And I think soil testing has been taught pretty poorly in the way that people can actually make use of it. So it's when it's taught in an agricultural way, and it's taught assuming that soils actually have some meaningful amount of CEC. That that's kind of the way that it tends to get taught in school, in soils classes, even when it's and it'll be just like one lecture out of an entire semester course. But the reality is, fine turfgrass is grown all over the world in sandy root zones. And if you're not growing turf in a sandy root zone, if you're growing turf in soil, then you probably don't need to worry about this so much. But um, the most highly maintained turf is grown on sand root zones. And the most highly maintained turf is what we're really concerned about, and we want to make sure that we get it absolutely right. And that's why I think it's important to understand what these numbers mean and what you can expect. So I will just say the numbers are used to figure out how much fertilizer to apply, and this illustrates this particular experiment where all of these started at one level and they finished much lower. The potassium in the soil started at levels of 20 parts per million for one sand, 58 parts per million for another sand, 71 and 80 parts per million. So four sands that range from 20 to 80 parts per million starting soil potassium. And at the end of the experiment, now we go all the way out to 65 days later. One of these sands was at 12 parts per million. One of them was 18 parts per million. One of them was 41 parts per million, and one of them was 44 parts per million. So I want to mention one more thing about how this works over time. first of all, when you do a soil test, you want to figure out how much fertilizer to apply to make sure that you don't drop below a minimum. And that's what the MLSN minimum is a level that we will make a fertilizer recommendation to make sure that we don't drop below that. That's what Jason Haynes's blog post explains, an easy way to think of that. Because I always say, like, plug it into the equation that I give you, plug it into the equation that I teach. But I know that, like, there's just, everybody objects to it. They say, oh, it's too complicated. And it's like, oh, okay, maybe it is too complicated. So we'll wait for somebody like Jason to be able to explain it much better. But uh, as we as we then soil test for a second time. And so I'm recommending to pay attention to keep track of how much fertilizer you apply over uh, the duration of time from the first soil test to the second soil test. So if you know how much fertilizer you apply, then you know what the maximum grass use of those elements could be, and you can see how those elements changed on the soil test. If the soil's changed more than you expected, if the soil nutrient levels dropped more than was expected, then you can figure that the soil is not supplying that element. And we can see in the chart that I'm showing on the screen right now, and I would encourage you to check this out if you're just listening to it. Two of these sands do not supply potassium to the plant. I mean, two of these soils, I'm using soils interchangeably with sand. Um, Two of these soils are not supplying mineral forms of potassium. And that's because they deplete rapidly from the soil potassium depletes rapidly, and it drops down to a level less than 20 parts per million. So I'm pretty sure that these sands are not supplying potassium to the grass other than what was already in the soil that had been added as fertilizer. But two of these sands, the BD and the CU sand, they appear to be supplying potassium to the grass from some mineral forms in the soil. So if we would work through the math, and maybe in some future blog posts I will do this, if we would work through the math and figure out how much these soils were expected to change based on how much the grass grew, based on how much fertilizer was applied, and we would find that two of these sands depleted the same amount or more than expected. So that means that they're not supplying potassium to the grass. Two of the sands, the BD and the CU sands, they appear to be supplying potassium to the grass from mineral forms in the soil. And then those are the types of sands that when you make that calculation at the time of the second soil test, you will realize that these sands are supplying potassium, and the fertilizer recommendations for the second sequence of fertilizer recommendations will be updated or should be updated to reflect the lower amount of potassium required as fertilizer, because we found out that the soil is actually supplying some potassium from mineral forms. So that's how this works. That's how I do the soil test recommendations, and I think that that's the best way to do it for turfgrass, and that's the best way to do it, especially for turfgrass growing in sand root zones. So I um, I I guess maybe this is incomprehensible or impenetrable to some people, but that's how I think about it, and that's something that I would like everybody to understand. So that is a recent blog post, and I would be interested to hear if you know a better way, because I or a better way to explain it. I know some of you who are listening to this, you know what I'm talking about, and you understand the soil test is just used as a way to make a fertilizer recommendation, because um, like I've heard other people. In fact, Larry Stoll has done something that he puts on the climate appraisal form that I don't really recommend because I find it a little bit misleading. Um, and he will make a calculation and say, based on the expected plant use for your site, um, in order to stay above MLSN, you might need to have a soil potassium level of 92 parts per million. So he'll show that 92 parts per million. But the problem is, if you don't have the cation exchange capacity that would allow the soil to hold 92 parts per million, then you could add all of that potassium all at once, but then it would rapidly drop through the soil, go out of the soil, and you would then actually drop below the MLSN minimum. So I don't like to consider the soil test levels as a target of like, let's target 75 parts per million, or let's target 50 parts per million, or anything like that. I'm just using the soil test result to calculate how much fertilizer needs to be applied. And the fertilizer, now Bob Rayleigh always says the efficiency matters. I'm talking about fertilizer as being basically applied uh, in proportion to how much the grass could use it over the time over which I'm making the fertilizer recommendation. Generally, I'm doing that for 1 year. So I'm not saying that if you need 10 grams of potassium, 2 pounds of 10 grams per square meter, which would be 2 pounds of potassium per 1,000 square feet. If that's your recommendation, then basically you would divide that, and ideally you'd apply a little bit every day in proportion to how much the grass is growing. I know that's not realistic. So you apply it as efficiently as you can, divided over the time over which the fertilizer recommendation is made. So you don't apply that 2 pounds of potassium all at once, because the soil can't hold it. So um, that's that's the way this works. And I'm going to keep working on trying to explain this until I can convince even more people. And I'm sure we'll have some conversations, and people will tell me, Micah, it's not making sense what you're saying. And then I will figure out, maybe somebody will tell me a better way to explain this so that it can make sense. And I'll keep practicing at explaining it so that it is very clear and everybody else has the same intuition about this than I do. I don't know. I mean, there's so much misinformation going around in our industry, and you've got so many people, well-respected people, that go give these seminars, and they're just saying things that are completely not true or that are terribly misleading. So you, if you're going to be misled, I don't know. Maybe some people are just bound to be misled, and they're happy to be like that. But for the few people who really want to understand how this works and do it right, uh, I would encourage you to keep thinking about this and pay attention to the things that I'm writing about, because if I get it wrong, I'm going to correct myself, and you will hear about that here on the ATC Double Cut or on my blog on nationturfgrass.com. All right, no more rambling from me. I will sign off now and be back soon with another ATC Double Cut, maybe with a guest, um, talking about some very interesting topics. For ATC from Tokyo, I am Micah Woods.